Hello, in this video, let's talk about feedback in circuits. Now, feedback is an integral part in design, and we'll see that negative feedback is the most common technique that is implemented in almost all analog circuits, and for the following reasons. Now, the multitude of reasons for which feedback helps, some of them I've listed here. First one is gain desensitization. Now, typically, when you have circuits, when you have to implement them on silicon, you have to worry about process variations, temperature variations, power supply variations that might happen on the board. And so you want to ensure that the gain of your circuit, for example, an amplifier, does not vary too much with process corners or with temperature or power supply. So you want to essentially have a method by which you desensitize the circuit to these variations. So feedback is the most common way to implement that. The other need might be to reduce nonlinear distortion. That is, we want to keep gain as a constant, as a independent of frequency, for example. So we don't want to introduce higher order terms into our output signal. And so this helps to ensure that there's no nonlinear distortion with it. Many a times feedback is used to reduce the impact of noise on the performance of the circuit, right? So you can design circuits which either reject noise or reduce the noise in the output signal. And again, that's implemented using feedback. A large part of feedback is also used to control the input and output resistances or impedances. We'll look at a few examples of this later on in the course. We also use it to increase the circuit bandwidth. Now, obviously, none of this comes for free. And so what happens typically is in feedback, what we do is we have have a trade-off with, in most cases, the gain. So to get any of these desirable properties, we normally give off some sort of a gain margin and achieve one or a few of these requirements in our circuit. So again, it's a matter of figuring out what's the best circuit and what's the best trade-off for your application. Now, how much of stability or how much of this you need, how much of this advantage you need really depends on the amount of feedback, right? And so by increasing the amount of feedback, you should be able to make these properties more desirable, right? So obviously you don't want to over design the circuit. So this is where I think the experience of the designer or the experience of the person who's working would come in, because he or she would be able to tell what is the optimum feedback that is needed so that I don't lose a lot of gain, but at the same time I'm able to achieve some of these requirements. Now, typically, if you look at a feedback structure, you would have seen this in other courses like control systems or signals and systems. A feedback system typically looks like this. You have as input signal, an XS, and it normally goes into an amplifier circuit, right? So let's this be the amplifier circuit, and you have an output. Now, what feedback does is you're going to sample some of the output of the amplifier and then convert that to a feedback signal, and that feedback signal is then subtracted or added from the input signal so as to generate this signal. So this is known as the signal flow diagram, right? And this term A is known as the open loop gain, and so typically XO is given by A times XI, right? So again, in most of the cases that we'll look in this course, this would be a linear function, that is A would be constant. So x0 would be some linear times xi. And as I mentioned, this feedback network beta, this network is sampling the output and sending a part of that output back to the input, right? And so we have a feedback signal that is generated, an xf, which is given by some beta times xo, right? And so what happens is that whenever we design circuits like this, an important factor, and this comes about especially when we design circuits, is that we assume that this feedback network does not load the input or the output of the amplifier. So what we're saying is that this beta or this network acts like a sampling circuit, in the sense that it does not load what's happening. So X0 doesn't change when beta is added to the circuit. That's what I mean when I say that it does not load the amplifier. So what we see at x naught is independent of whether beta is present or not present in the circuit. And so negative feedback, as I mentioned, is what we'll be looking mostly in the course. Negative feedback reduces the signal that comes at the input amplifier, right? So this XF is subtracted from this input signal, and what you get is this XI, and this XI is fed into the amplifier. So negative feedback is essentially associated with how XF interacts with the input signal. And when the feedback signal is subtracted from the input signal, that is known as negative feedback, which is what is most commonly used in our circuits. Now, let's look at the closed loop gain. And again, this we have discussed in when we discuss frequency analysis. So if you look at this kind of a structure, the closed loop gain, what I mean by closed loop gain is the gain from XS to X naught. The gain from XS to X naught is going to be given by A and with a feedback network, so A subscript F, and it's going to be given by A divided by 1 plus A beta. Okay. Now this A beta is known as the loop gain. That is what happens when a signal just traverses through this loop without any submersion. So this gain is known as A beta, and what we see is when this A beta is much greater than 1, the gain in the feedback system is just reciprocal of 1 of beta, right? So the feedback gain approximates to just 1 by beta, right? So which means that this beta limits the gain of this system, right? And this is a assumption we'll use a lot when we start solving circuits. Now when A beta is greater than 1, what does that mean? That essentially means that this feedback signal and this input signal are very close together, or in other words, this Xi is kind of like an error signal, and this error signal is very, very small, and so the input to the amplifier Xi is actually going to be Xs divided by 1 plus A beta, right? And so when this A beta is very large, this Xi is going to be very, very small. Now the polarity of this A beta defines the type of feedback, and it's an important parameter. We'll come time and again to it. And this A beta has to be greater than 0 for a negative feedback. Now, as I mentioned today, as A beta increases, the feedback gain comes close to 1 by beta. So therefore, the magnitude of A beta determines how close this AF is to 1 by beta, right? So if A beta is very large, then you can approximate AF to be 1 by beta. And so this magnitude of this A beta is essentially kind of a measure of the amount of feedback, right? So the more the value of A beta, the more we think is the feedback that's happening in the circuit. And what the other point that illustrates this is we'll see that the magnitude of the various improvements that you'll see, be it the bandwidth, be it the input resistance, etc., are all going to be proportional to this 1 plus A beta term. So this A beta is an important term because that determines what's the amount of feedback that you have in your system. Now, a thing to keep in mind, especially when we start doing frequency analysis of these circuits, is that as a function of frequency, A beta can become negative, which means that what you initially thought was a negative feedback can become a positive feedback, right? And then essentially what we say is that the feedback becomes unstable. So you have to be very careful, especially because when we deal with circuits, we're dealing with capacitances, we're dealing with poles, we're dealing with zeros. And so it's possible that A beta can go negative, right? And in that case, you have to be careful because at that time, what you assumed was the feedback has essentially changed. Now, how does one determine the loop gain of a circuit? Now, again, if I look at this signal flow diagram, to determine the loop gain, what we do is we break this circuit at some convenient point, right? So we initially set the input signal to 0 because this loop gain is a property of the circuit we've designed. It's independent of what the input signal is. And we break the feedback at a convenient location such that we can individually estimate the values of A and beta, and that A and beta do not change when this break occurs, right? So here again is a skill that comes with experience as to where do you break this circuit so that because of this break does not change the intrinsic properties of the circuit. And then what you do is apply a test signal at the input of beta or the input of the feedback see how that signal traverses, and basically measure the return signal, which is XR. So you apply a test signal at the what would have been the output of the amplifier, and you measure the return signal outside the amplifier. And so this essentially is the ratio of that XR by XT, or is essentially going to be your A beta. And in this case, if your feedback is negative, what's going to happen is that because of this negative term here, you're going to see that XR and XT are essentially going to be out of phase, right? Or in that XR by XT is a negative term. So only if that is true, then your loop gain is positive, indicating that you have a negative feedback in your system. Now let's look at some of the properties of feedback. So first example is, let's take the gain desensitization. So here we looked at, when we have a feedback circuit, the gain is given by A by 1 plus A beta. In other words, if I'm going to look at the differential of AF to A, it's essentially the differential of this, which is 1 by 1 plus A beta the whole squared. What does that mean? That means that if I'm going to see small changes in A, right, suppose the amplifier gain changes due to either process, due to temperature, due to something, input power supply, whatever you have it, the relative change in the feedback gain is going to be reduced, and it's going to be reduced by a term of 1 by 1 plus A beta. So if dA by A is going to be 1, then dAf by AF is going to be only 1 by 1 plus A beta. And as your A beta increases, this term is very small, indicating that the variation in AF, because of whatever is causing the variation in A, is going to be substantially small, right? And so this is what is known as the desensitization factor. So this 1 by 1 plus A beta is essentially the gain desensitization factor because of the feedback they've attached in the circuit. Let's look at another example, say the bandwidth extension. So let's assume that we have the open loop gain A as some single pole circuit. So we can use a dominant pole expression. So I can talk about a midband gain divided by 1 by 1 plus S by omega P, where omega P is the pole of the circuit. Now if I look at the feedback gain, it's going to be given by AS by 1 plus beta AS, and here I'm making the assumption that this beta is frequency independent. So when I do that and do the math, I get A of S as AM by 1 plus beta AM plus S by omega P. And if I recollect the terms such that, I get what I want, what I see is A of S is AM by 1 plus AM beta. So this is going to be the midband gain of the circuit because of feedback, divided by 1 plus S by omega P into 1 plus A beta. So what's happened now is, because of this feedback, your pole, instead of bit being at omega P, has now shifted to omega P into 1 plus A beta. So remember, A beta is a higher number, so this pole is going to be a higher frequency. What has happened instead is your gain is reduced. So because of feedback, similar to what we saw in the cascode and CS amplifier, though that's not happening because of feedback, what you see here is that this gain, the midband gain reduces and the bandwidth increases. So you're trading off the midband gain to the bandwidth of the amplifier. Now let's talk a little bit about the sense and return mechanism. That is this circuit beta, right? So beta is sampling an output and returning a feedback signal to the input, right? So this, and again, in circuit design, we have only two quantities to worry about: a current or a voltage. So either we sample an output voltage, return a voltage or a current, or sample an output current, return a voltage or a current. So there's essentially only four combinations to worry about. So now, how do you sense a voltage? To sense a voltage, you want a circuit which works like a voltmeter. That is, it is connected in parallel across the two pins, right? And ideally, it should not load the output. So if this is your amplifier A, right, my feedback network should be like a voltmeter which does not load this output. And because this voltmeter is connected in parallel, this is known as a shunt feedback. Similarly, if I want to sense a current, right, if I want to sense the output current in the amplifier, I would be connecting whatever is my sense circuit in series, because I need it to work like an ammeter. I need this output current to flow through my circuit, which senses the circuit. So here the circuit is going to sit in series with my output load. And so here we have what is known as a series feedback. So whenever you sample a voltage, you're sampling with what is known as a shunt feedback. When you're sampling a current at the output, you're sampling with what is a series feedback. Now, when you want to now add these signals at the input of the amplifier, right? We have that summation term in the signal flow diagram. We can either do the addition in the voltage domain or a current domain. Again, we're dealing with voltages or currents. And so when you want to, and again, this is from very basic electrical sciences, when you add voltages, we typically connect them in series. And when we add or subtract currents, we connect them in parallel. So if I have an input signal and a feedback voltage, I would connect them in this fashion, where both my generated voltage is connected in series with my input voltage. However, if I'm doing a current feedback, my feedback current is going to be connected in parallel to my input current. And so we see that the voltages are added in series at the input of the open amplifier and the currents are added in parallel. So please remember this, that voltages are sensed in shunt, currents are sensed in series, voltages are added in series, whereas currents are added in a parallel or a shunt fashion. Right? And so what we have are examples, for example, of voltage sensing. So here I have an amplifier, right? And one way to sense the voltage is a very simple way would be to use a resistor bridge. So what happens here is that this is your feedback network and the voltage appearing across R2, right, is being sent as the feedback signal to your summer, right? And again, if you look at this, this voltage V out is going to divide itself across this R1, R2 pair. If I look at a current, say I have some sort of an output current, then that output current, if I want to sample as a voltage, right, I would take the current, flow it through a resistor. So hence this generates a feedback voltage, which is the node voltage at this point. And I can send that back into my summer so as to where I'm sampling a current by converting it to a voltage and then sending the voltage back. Now, how do I do voltage addition? Again, you have different techniques. One way would be a differential amplifier, because we know that in differential amplifier, the output of the differential amplifier is going to be dependent on the difference between the two voltages on the differential pair. So here what I have is an output voltage being sampled, and then this output voltage is fed back through VF to one of the transistors of transistor pair. So this pair is essentially implementing your subtraction of the signals. Another way would be using the VGS of a transistor. So here I have the input voltage connected to the gate, and here I'm taking the output feedback signal as a voltage and connecting it to the source, right? So as my feedback voltage increases, my effective VGS decreases, right? So this current that is flowing through the transistor is going to be a function of Vin minus Vf. Similarly, the gain of this differential amplifier is going to be a function of Vin minus Vf. So these are ways by which you can implement the subtraction either using a differential amplifier or using a VGS in a transistor. So if you want to do current addition, a simple way to do current addition, and we've looked at this again when you've done op-amp circuits, would be to essentially have a feedback current that flows through a RF, and this RF can be connected to some voltage output here, where the current through RF depends on the voltage that's connected at the other end. Another way would be to take a voltage at the output and convert it to a current by using a transistor. So here what you're doing is this feedback signal shows up as a feedback current in both these cases. So given that you can sample a voltage and return a voltage, sample a current or return a current, there are four kinds of feedback topologies that exist in circuit design. When you're sampling an input signal of a voltage and the feedback signal generated is a voltage, right? So you're sampling the voltage at the output and returning a feedback signal of a voltage. This is known as a series shunt topology, right? Whenever you say the topology, it's always with what's happening at the input and what's happening at the output, right? So here the input is a voltage. So we're adding voltages in series. We are sampling voltages in shunt. So it's a series shunt topology. Similarly, if my feedback is a current, right? If I'm adding currents at the input of the circuit, but I'm sampling a voltage, right? So my input is being a shunt, my feedback is being sampled as a shunt. So this is going to be a shunt topology. Similarly, if my input is a voltage, right, but my output is a current, I'm sampling a current and converting it to a voltage, then it is essentially a series topology. And finally, if I have an output current which is being sampled and sent in as an input current, then I have a shunt series. So remember, the topology always goes as what's happening at the input and then what's happening at the output of the open loop amplifier, right? So this indicates how the signal and the feedback signal are added together, and this indicates how the feedback signal is sampled from the output signal of the amplifier. Now what we'll do in the next few videos is we'll discuss these individual topologies in detail.